on this computer. Perfect. So let me start sharing my screen. Perfect. Okay, so let's reorientate ourselves. People still coming on Zoom. Okay, so this is our homepage. I'm going to keep looking behind me, but we don't have a projector today. We're only on Zoom. I am recording. I am sharing screen. Let me just, yep. Okay, so we are on Rockefeller University.github.io. This is our homepage, and it's here. You will find most information about us. Really, certainly on this page, our homepage, you'll find all the information you need on the course. So just to reiterate what we're covering in this course is very practical, high throughput sequencing. It's kind of tailored around. It's the biggest part of really still data analysis and bioinformatics. And we are going to teach you everything you need to know to undertake common high throughput sequencing experiments. And this includes ChIP-seq, ATAC-seq, RNA-seq, CRISPR screening, which is becoming more and more popular, and scRNA-seq. Okay, so single cell RNA-seq, ATAC-seq. I do have here a genome assembly course. So this is actually a course which we host, but is run by the VGL. So that will be run later in the year. It won't be part of our session for the graduate school because it's quite specialist. But if anyone here wants to attend, please just reach out to me. Reach out to me here or here, and I can talk with Matt, who runs this in my team, and we'll make sure you get on that course. Another useful thing here about the page, videos. So we have our videos. I'm going to pause. There's Matt. So I've already started adding our videos. This is a hybrid class. You know, I expect you just to follow along as we go. So we have our part 1 and part 2. This is just our first and second session from last time already up. And I'm putting these on Dropbox too for Kristen. So if you ever can't, for whatever reason, get to our YouTube page, you always should be able to. Kristen will always have a copy of this too. Okay, nope, that's my private stuff. So we're in Intro to R, and if we click here, we have our courses. Again, getting help here. Session 1, we were, well, some of the way through. I think we just finished data frames. We did an exercise, and we're just about to do lists. So I just want to do a quick recap. And we won't do recaps every session, but because we're learning new objects, this is actually at the start of next session, so we'll skip it then. So we've already come across the first 4 of these main data types, and that is vector, an ordered collection of a single data type. So it needs to be all numeric, all character, or all logical. We know we can create a vector using this combine function as one way. We had other ways too. But we can combine and we can put the values we want to create a vector from, separated by comma. We can then turn our vector into a matrix, which is effectively our 2D version of a vector. So it's a table, and it has to be a single data type. So it all needs to be numeric, character, or logical. Maybe there are other data types I'm excluding there, but it all has to be one data type. So to create a matrix, we usually run this. We do matrix, give it a vector, and then we need to tell it how many columns, how many rows. I guess these are important properties of a matrix. And importantly, we have to tell it how to fill the matrix. So by default, it's going to work down a matrix of 2 columns and 5 rows, and it's going to go from the very first column and work down. Hey, David, I'll introduce you in a second. Perfect. Yes, so it's going to go down the columns. If we set by row, it will work along the rows while it fills it up. Okay. But then we came across factors. So factors are basically a slightly complex version of a vector, and they are a categorical vector, right? So they allow us to store data as categories. And to do this, we basically take our vector here, we wrap it up in another call called factor to turn into a factor, and we can set the levels that we want to be in this particular factor. Okay, if we don't set levels, by default, it will set the levels to be the alphabetical unique values within our vector. Okay, and we saw that can be quite important. We saw how we can update them, and when we start to do ggplots and various plotting, it's going to be important to control these levels. The last data type we saw was a data frame, and the data frame is fantastic because the data frame allows us to hold different types of data in one table. Okay, so we can hold numeric, we can hold factor data, character data. They can all be mixed, and we can still operate on the various columns. If it's a numeric column, we can still apply a sum, a mean, arithmetic operation. Whereas a matrix, we know once we turn one column into or even one value into a string, the whole matrix will become the arithmetic. So data frames, much like a matrix, but allows us to hold different data types. We saw that we can access information from vectors using square brackets. So if I want the 10th value, I can do square brackets 10. That gives me the 10th value. And I can not only just pull out the 10th value, I can reassign a value within my vector. So here I say 10, and I can assign now 0, and the 10th value in my vector has now become 0. Okay. So we can use square brackets here to index a particular element from a vector. We can do the same from rows and data frames, but to access a row or matrix or a data frame, to access a cell, a row or a column or a particular cell within a data frame or a matrix, we need to use two coordinates, two indexes, and that would be a row index and a column index, right? So if we want to get here, say first row, first column, we would put 1 here and 1 here. In this instance, we can also pull out, here you go, 1, 1. We can also pull out whole rows at a time by just putting the index for the row, comma, nothing in the column, and that pulls out the first row. Or we can pull out first columns, here doing comma, 1, and that pulls out this first column. Similar to vectors, we can assign individual values for cells, or we can assign whole columns at a time. Here I'm assigning the second column to be all 100. Okay. Again, slight word here about why matrices are different for data frames. In this case, I build a numeric matrix. We can see it doesn't have quotes around the values. It means they're numeric. As soon as I change one value in this matrix, and here I just change our first row, second column to a word. So I add one character to my vector, my matrix, and the whole matrix now is a character, right? This 1, even though it's, well, let's say this 3, it's not in the same column, it's not in the same row, but the whole matrix got transformed. And this is kind of a base thing in R. Matrices, we want to be able to operate on them as if they're the same data type. Data frames, we expect them to be different data types. We also saw we can use logical operations on these things. So if we want to take our numeric vector, do simple logical operations greater than 9, and that will just tell us which values in our vector were greater than 9. Here it's just the last one. And we can do the same type of operations working on things like columns here from a data frame. A data factor equals R. It's just going to pull out the rows here where our factor value in this column was R. So the first, the third, and the fourth. With these logical operations, then we can actually start to use subsetting, so we can just extract values from our vectors. And in this case, I'm going to use logical subsetting just to index all the values in the vector which are greater than 5, and I'm going to assign a new value to them. Okay, so here, just using the A vector greater than 5, assign 10, and then the values from 5 above, which is this one, 6, 7, 8, 9, 10, they all got assigned 10. One last worry here, and I'm just going to pass this to the last thing I'm going to cover. when we were starting to replace things in factors or data frames, we saw we had this potential problem, and that is if we are trying to replace a value in a factor, so here we only have the values R and Python. If I try and replace something within a factor or a data frame column, which is a factor, in this case, I'm going to try and put not Python here. Okay, so I'm replacing every row where factor is R, and I'm just looking in the second column, which is R, this column here, the factor column. And I'm just trying to replace these values, which were R, with not Python. It gives me this warning, invalid factor level generated, and that's because not Python wasn't listed in the levels. And it's just giving me NA, NA, NA. Okay, so it just didn't work there. To fix that, we need to set up front or change later the levels of my R factor. And here, even though we only had R and Python in there, I also added a level for not Python. And then when I went and tried to replace every value which was R in that second column with not Python, now it worked. And the reason it works is because I set the levels. Great. So that's just a very flash recap of our first session. Again, we're going to be applying and using these over and over again. So you're just going to learn how to use them as we go along. So I just want to take a moment. David, can you come down for a sec? Can I introduce you? As you may notice, David, we don't have what's it called? Projector working today. So if you don't mind, I just want to introduce you on Zoom to people. So you're going to have to come be here for a second. So David, just say hello.
Hi, David.
So David Rakina is in Sandy Simon's lab. You're in your 5th year there now, right? 6th year now. So he's done his PhD in that lab, and you joined us for our first year here.
Yep.
So you've been here you've been with the course as long as the course has existed. But he has real practical experience in applying R to real data analysis. So feel free to ask David. I'm going to say this for you, David. Feel free to ask him any questions on the course especially, but if you want to talk a little bit outside of the course, David's a man to talk to, really understands, and really put it into practical. Thanks, David.
Thank you.
Sorry, I'm not sure, David, maybe you have it. Do you have a Mac?
Yeah.
Do you have a USB to HDMI cable? So 1 second, folks, I'm just trying to set up the projector. I used to always have one. I lost it. Oh, you're kidding. Okay, let's see if we can get this working. Sorry, 1 second. I'm just setting up the room. I'll email Kristen to tell her I resolved that now, hopefully. Coming. Amazing. Great. Thanks, David. Okay. Share screen again. Back in action. Okay. Hide myself. Okay. So then we've gone up to most of the major data types. Is that all good, everyone? Yeah. It's a bit bright, actually, doesn't it? So we've covered some of the major data types. And the last data type we really want to look at is lists. So lists are great before we get into things like complex objects, because lists allow you to hold different data types together in one object. So if you need to orient your data together, make sure you're keeping relevant metadata with a matrix, which it relates to. Lists are fantastic for this, right? So it allows you to hold data types of different types and unequal lengths, all in one kind of object. So we'll create some lists, some objects we can put in there. So we'll create a vector, 1 to 4, create a matrix. This is going to be an entirely numeric matrix, and then we'll back on time. We'll create a data frame, and then here I will put a numeric vector and a character vector. So if we want to create a list from objects we already have, we can just use the list function. Hey, we can just use the list function, and we can just place within there the elements we want to create a list from. So we have list. In this case, I'm just going to put the first element, so our vector, and then I will put our matrix, and then I will put our third element, which was our data frame. And you can see if I print the list, it looks a little unusual. First, we have kind of our first element in double square brackets, which is unusual, right? We haven't seen that before. But then within there, we have our vector. And then we have in our second element, double square brackets number 2, so our second element, we have our matrix, right? And in our third element, we have our data frame. Great. So just as with vectors and other things, we can provide names to this. And the easiest way to do that is when we create the list, we just provide a name for what we want to call them. So here, I'm going to have first equals, and I will give it my vector. Second equals, and I will give it my matrix. And third equals, and I will give it my data frame. Right? So now when I have a list, it doesn't show this element, right? It's actually showing the names of the elements. So I know that first corresponds now to my vector. Second will correspond to my matrix. And third will correspond to my data frame. Lists, as with other types of data in R, they can be indexed, but in contrast to standard data types or other data types, using the single square brackets on a list is going to return to you a list. Okay, so that's, I think when you first do this, kind of frustrating, because you're going to do my list 1, it's going to return to you a list, but not the actual vector within the list. Okay, the reason they do that is this is the only way you can retrieve a range of positions, right? If I want to retrieve a vector and my first and my second element, I want to extract them as one common object. There is no object other than a list which can hold them together. Right? They are different. This is a vector, this is a matrix, right? So they need to be in a list if I'm going to extract more than one. So by just doing square brackets and 1, I extract a list which contains my vector. If I want to actually get to the vector within that list, I just do double square brackets. I name the element I want to extract, and now I actually get my vector. Slight contrast to this, and again, this is because when you do double square brackets, you can only pull out one element at a time. With single square brackets, you can pull out multiple elements within a list. If I want to pull out the name by name, again, I'm only going to be able to pull out one, because only one element is going to have. So if I use the name, I'm going to pull out just the vector. Okay. Because we're using the dollar here, I'm not sure if I say this in the next line, but because we're using the dollar here, like data frames, if the name is unique enough, I can just type in FI, and R is clever enough to say, okay, that couldn't be anything else from my list of names, and it will just pull out the first. Again, similar to vectors, lists can be joined into bigger lists. I can combine two lists into a bigger list, which you can imagine will be useful. One holds my data frames, one holds my matrices, and now I want to combine them just by using this C function. So here I have my list I've created called my name list, and then I'm going to combine to it another list I'm creating here. And this list just contains one element called fourth, contains the vector 4, 4. If I combine them together, I get a new list. I'm just subsetting this here, indexing this using single brackets to pull out the first and the fourth. You can see we have that element, and then we've added to it at the end the element from our second list. Worth noting that if we combine a list with a vector, it does something a little bit more unfriendly, and actually what it's going to do is break up the vector into individual list elements. I think most of the time people don't want to do that. The reason you're attaching this is because you want it as an element. But in this case, if I do C and I attach a vector, you can see we end up with a second and a third element. Okay, so we don't want to do that. A function which is often a thing we want to do with lists is to kind of flatten them. We want to put them in a different structure, really because we want to operate on them like a table or like a matrix. Okay, so sometimes you will run a function and it will return to you a list of values. In this case, we're going to create this list 1, 2, 3, 2, 6, 7, 1, 4, 7. And we have our named list first, second, and third. I can turn any list into a flattened representation of it, especially if it contains just vectors here, by doing unlist on my list of vectors. And now I get back a vector, the same length as all the elements in the list, and it's just strip them out and put them into a flat list here. And I'm just showing the first 7, so run out here. But you can see it also does something clever. When I unlist this, it also assigns a name to our elements. So the vector, the first one's called first 1, first 2, first 3, and it's taken that name from there, and then it's just applied the position in that part of the list. What we'll often want to do with this, though, is take a list, and I'm showing you this really because we're going to do this later on, is we want to take a list, flatten it, and put it into a matrix. Okay, and it may be that we have a bit of software which returns some values, which we then want to put into another piece of software. I think someone might be trying to come in. Oh, no problem. I'm secretly expecting someone to come up with a USB-C adapter again, because I asked for that at the beginning. So we'll do list first, second, third. We unlist this, and it will become this flattened list here. And a common operation is to take that flattened vector, use our matrix function again, and just set the number of rows here the same length as the list. The number of columns, we know that there should be 3. I'm going to tell it to fill by row, and then I can just assign some names to this here, and I'm taking the names from my list. So we can turn, you know, a list like, I don't actually have a list, but a list like this into a matrix fairly simply. And the reason we'll do this, as you'll see later on, is when we're combining values across lists into one big matrix, maybe it's counts from RNA-seq, and then we can operate on this with all our matrix operations. Cool. Okay, so a list is just our general container. And as you'll see later on, it's a great way of holding elements related to the same kind of experiment sample into one nice container. So before we move on to reading in data from external sources, some useful things we can do to kind of manipulate our classes. So I've shown you a vector, I've shown you a matrix, I've shown you a list. If we want to know what the class of a variable is, obviously we can type it in and look at it. It will tell us, right? We can also use this function class on whatever our object variable is, class, named matrix. And it's going to tell us here it's a matrix. This is a second type of object you don't need to worry about. If I've got a data frame, I do class, it tells me it's a data frame. Okay, this can be useful programmatically. Sometimes I might need to check before I run a particular set of functions. I just need to make sure it's a data frame. Most of the time, you'll need to make sure it's a matrix because of these great rules, like matrices can be all numeric. A lot of programs, like our RNA-seq programs later, are going to insist that the class is matrix. If we need to move between them, so we have a data frame, it contains all numeric values, and we want to turn it into a list, or we have a matrix which we want a data frame version, so we can use it in ggplot and plotting. We can take advantage of this as dot, and then the class we want to turn it into. Okay, so most of the time, this conversion, the most useful conversion here is actually matrix to data frame, data frame to matrix. But in this case, if I've got my matrix and I want to turn it, say, into a character, I can do as.character, and then it just works down the columns and turns it into a long vector. I want to turn it into a standard kind of numeric, I can just do as.vector, and it just extracts the values and puts them in. Like I was saying, probably the most useful one is as.matrix and as.dataframe. And in this case, I can just do as.dataframe on my matrix. And it's then going to turn that into a data frame class. It will contain the same information, but it just means programs say, I need a data frame or I need a matrix. They're going to. I'm not sure this is the best thing, but if I do as.list, it just breaks up our matrix and puts every element. Okay, so that's a little bit about the data objects we're going to come across, and then how we can kind of manipulate. Okay. So most of the time, you're not going to be generating your data in R, but we'll be importing your data from external files. It's the reality. Even data you're generating in R, you may normalize your data, create bigger versions, smaller compressed versions, but usually we start from external files. And we're going to show you how you can deal with some of the specialized formats of data, aligned data, bigwig data, genomics data, generally later in the class. There are special functions to deal with them. But if you weren't doing genomics, most of the time we're going to be getting data from something like this table. Okay, so we're used to looking at data in things like Excel, Prism, these all use tables. Right? So it's a good way for humans to review data. This is a standard kind of format. We will have a metadata row column, and we will have often, and we have rows and row names. Here, the concept of that in R, but here we will have our gene names. We have all the gene names going here. So this is gene G, and these are the expression values for it. And in the remaining columns, we will have our samples. Right. We want to get that into R in some format so we can start to operate it. And I think if we look at this, we know it's a table. So already we would expect to be able to try and put this into a data frame or a matrix, right? Making sure I'm still sharing. We can easily read tables from text files, which is often what we're going to be dealing with, using this read.table function. Just to take us a little bit into R, I'm just going to stop this for a second. I'm just going to do a question mark read table. We can look at the help for this. And what we'll see is actually there's a whole family of read tables, right? There's a read table, read CSV, read CSV2, read delim2. I think in reality, these are all just extensions of read table with some defaults set for you. So read CSV sets the default separator in the file to be comma, because CSV stands for comma separated file. I think delimited files typically be tab separated, so it just sets you tab. Okay. We are here just using the kind of base version of this, and this is read.table. And we need to set two important parameters. One is sep, so separator, and this really tells us what is the separator between columns in your table. And in this case, it's a comma. So comma separator files like this, CSV. TSV is usually using a tab to separate. For tab, programmatically, if you want to describe a tab, I mean, you can't really type in a tab into R, but it's \T that represents a tab. In this case, we're going to read this table. It's going to be separated, comma. I'm going to say header equals true, and this means that the first line in my file will be read in and set as column names. Okay, so they won't be part of the actual file. Hopefully, we can already see that's kind of important because, you know, if we want to maintain a matrix, we want it to be all one type of data. This is going to be character, and this is going to be numeric. Right? We may have a column here which is all character, but we want to assign these to column names because these are the types of things we want to be able to pull out, index our columns in our table by the sample name. Another really useful function which I never used to take advantage of, but it's really useful, is this row names function. Okay, so the row names function is going to save you a lot of hassle. Okay, so in this case, we're going to know, I know from having seen the table, or perhaps from having read it in already and being disappointed that I've got gname here, I can actually upfront say, I want the row names of my read in object to be the first column. Okay, so if I say row.names equals 1, I don't get this as a column in my table. It's now automatically set as row names. Okay. So, you know, already something very, very useful has happened now. This table only now contains numeric values, right? So I can turn this into a matrix. I don't need to worry about things being mixed characters and numeric values. And that saved me having to then take out the first column, attach those row names, and all this, right? I've done that in one line. Okay, so this is an interesting thing, and it kind of slightly predates our class, or it's to do with the fact that our class predates a big change in R. Data which is read through R from read table will be a data frame. Okay, we want to be able to turn it into a matrix, so we can do as.matrix with this trick here. It's all numeric. That's great. The issue here is, sorry, got someone coming in. It's exciting, isn't it? I'm going to give it a sample. When we create data frames, it's actually going to try and turn, especially if we read it in. It used to, and it's changed now, but it used to try and turn anything which was string. So if we had a column of, say, names, it would automatically turn them into a factor for you. Okay, so now telling you what I said earlier on about factors, and then it's very hard to replace new values and factors because we need to worry about the levels. This was actually a little bit of a pain. And it used to be that when you do read.table, a lot of the time you would need to say strings as factors as false. So when you read in my table, please don't convert character columns automatically to a factor form. Okay, that actually doesn't affect you anymore. I think strings as false is now default. But it used to be a pain. So if you're working on an old version of R, be aware of this. As we will see when we get to plotting, strings as factors is kind of an important option, but we'll show you that when we get there. Two other really important lines, and I think we're going to talk a little bit about these as we go along in the exercises, are skip and comment char. Okay. So skip, you may know that the first 4 lines of my file are always junk. I don't want to read them. Okay. Skip allows you to skip a certain number of lines in your file and then just start reading from there. So if you know, and we're going to show you this later on, like Homer peak calling files, when you're trying to identify transcription factor binding sites, first 5 lines is always nonsense. Comment char is really useful as well. So comment char effectively says which lines to skip. And if a line starts with whatever this character is set as, it's not going to read that line. Okay, and again, really popular programs like Max, all these peak callers, what they tend to do, because they know that most programs follow this rule, they will put their kind of instructions on how this like file was created at the very top. So they'll actually put the program file command. That will be commented with a character in front of them. And then if you set the correct comment char, you won't read that into your file. So skip and comment char are really important. And I have some great exercises today, which will show you kind of how best to use this. So read.table is actually kind of powerful. It can also read data directly from HTTP. It can also read data, I believe, directly from zip files. So this is all kind of built into R. You don't have to worry about it. So here I put something on our GitHub. It's just the same file we've read without any specification about downloading it or anything like that. It knows it's HTTP or HTTPS or FTP. It will do the correct protocol and it will read it in for you. There is, and I haven't tried this myself for a while, but there is also the option if, that can be very useful, if you've got Excel open and you want to copy a bit of the table to your clipboard, you can actually just do then read.table file and tell it clipboard, write it out like that. And it will read from your, whatever you've copied, whatever's held in your copy before you paste it, and it will read it into R. So read table is very flexible. But by default, it's also, wants stuff to be in a very tabular format. So something we're not going to use much in this class and never again, I just want to give you a little view of it, is scan. Okay, so scan, I think we can look at the help, is a very low-level function for reading data in R. And what scan allows you to do is not just set the file you want to read, but you can also tell it up front what the type of data is for every column. So here, I'm telling it the first column is character, and the next 6 columns are numeric. Telling it to skip the first line. What that allows us to do is just read in data a lot faster than read delim. Okay, and that's because read delim is checking your data as it reads it. Scan is believing you. When I tell it the first is character and the next one is 6, next 6 are numeric, it's believing me and it's going to try and create a file where those columns are all numeric. So you need to be absolutely right. We're not going to use scan in this class. Apart from when we get to BAM files, how we handle aligned data, then we're going to come across something called scan. Okay. So I just wanted to show you it exists. The real difference is we have to use this what argument and we have to tell it what every column, what type of class we want it to be, character. Once we've read our data in R, most likely we're going to want to export it and we're going to want to export it to a file. We can then open in TextPad, Excel, OpenOffice. So just like we have read.table, we also have write.table, which is really useful. And we can just give it the data frame or matrix we want to write. We give it the file we want to write to, and then we're going to give it the separator. Okay, important to give it a separator. If you don't, it's just going to do nothing, no separator, and it's going to be impossible for you to open it in anything. So I think here we're going to put separator with comma. That's a good file. We should be able to open it. Often our data will have column names. By default, these won't be included in the output. We also probably have row names, and I'm not sure if I'll probably show you this problem here actually. Row names, column names we will often set to be true. If we want them, we will write them out into our file. If we have them, we usually want them in our file. Row names is a little bit of a problem. Maybe I can show you this actually practically. I can give you an example. Let's try this. So I'm just going to set myself up here. I'm going to make this. So now I have, this is the annoyance, I read it in, but now I have a table. These are my row names. I do write.table. Table. Table file equals comma row dot names equals true. Okay. I'm trying to open that in Excel. All right, go to this open new terminal. Open selected. Sorry, I'm just trying to get to this directory. There we go. So you can see already this is a problem, right? Because I've written out row names, I actually don't have as many column names. Right? I've got column names here. You can see sample 1, sample 2, sample 3, sample 4, sample 5. But I'm missing my last one. It's because my column names have shifted over by 1. Right? And that's because I didn't have a column title for my row names. So basically, every time we write these out, we're going to have to do insert whatever cell and shift these along. So this is a problem, and you need to kind of fix up your file, either assign your row names to a column, then write it out, give them a proper column header. Otherwise, you're going to get files like this, where your column headers are off by 1. And then it's just a pain, because someone will open it up and they'll get confused with the result. They'll be looking at the wrong column. It happens to me a lot. It's a really simple mistake to make. Okay. So the importance of writing out with row names equals false. So it's important to know what your data is. And often you're going to have these big tables, and you just want to see a part of them, maybe this top or the bottom. So you have two really useful functions inside R, which is head. If you just do head on your table, it will show you a certain number of lines. I think by default, oh, there it is, 6. Okay, so there's actually an argument in head, n equals, we'll tell you how many to show. Tail is often useful as well, because open a file, you can often see the top. You don't necessarily check the bottom, and this will just show you what is at the bottom of your table. There you go. There's also, I think, a nice feature inside RStudio. If you kind of click, if you go to your environment and you have a table, I thought it was somewhere here. There you go. You can also view it inside this kind of top panel here. So if I just went to the environment and I find my data, remember that's not going to be, if your table is huge and you try and open it inside that little R window, it's going to slow down your computer. So often just head, table. It's easy enough. Oh yeah, let's try that option. Head table n equals 2. It shows me the first 2 lines. Okay, what are we doing for time? 20 minutes. So in our first year here, I think it became one of the big requests for the course. And please, if you have requests for the course, let me know, because we genuinely do update as we go along. It keeps the course exciting for me. One of the requests was this RIO, Rio. This package is really, really incredible. So what they've done is they've taken all the work other people have been doing to try and read in XML. So XML is really important if they're going to do interacting with databases, but also MATLAB, SAS, SPS, Minitab. Pretty much if you're working in a different statistical package and you just want to try it out for a bit and then go back to it, Rio allows you to import and export to these formats. I don't use much SPSS, SAS, MATLAB, so I'm not going to show you that, but I can tell you it does. Excel, I like OpenOffice. It allows you to support these formats too, and that is important. Because being able to import from Excel, but also export multiple tables to Excel, can be really useful. So great. The first thing we need to do then is actually install a package. Okay, so I don't think we've done any installation yet. And there are a few ways that we can install packages. One of the easiest ways from any R, don't need to be in RStudio, is just install.packages, and then in quotes, you do the name of your package. So here, RIO. What this will then do, it may ask you to have or choose a mirror. Just choose the one in the same country as you. And then it will go, it knows not only where to find a package, but it knows to find all the dependencies for that package. Okay, so that package, as I just said, covers all these formats. The authors of that package haven't written all the programs to read in all those formats. They are using other people's packages. Install.packages will go get everything we need. Really cool. So another way we can do install.packages, so this is your packages here. It's in our tab here. These are all the packages available to us. If we want to install a package, I never really clicked that button, but there should be a tools, install packages. I think I can just do, it's doing a live search for me, right? So it's actually searching CRAN, the repository, and it finds Rio. I'll do that there. I can just do install. I've already got it installed, so I'm not going to press it again. So yeah. Because they're newer. Yeah, so say no. No. Yeah, so actually I'll talk about that now. It's a big question. It's a big question. Yeah, no. Can I cancel that? Sorry, got a question. That's a good one. No, actually, I don't think. I usually just try and use my knowledge of America to find out where's closest to us. I'm not sure if it makes that difference, but I just choose the first in the lists of the USA. Okay. Where's David gone? Hey, David. Yeah, do you mind keeping an eye on the chat? Because I often miss it. Just jump in on anything to that. Okay. So that having been installed, we can then load a package directly here. And I'm going to do this. Yeah, I can just click this. It's going to say library Rio. It actually types this in for us, and it's going to load that package and all the requirements. Talk a little bit about what someone just asked there. So when you install a package, CRAN is the repository. It holds all these packages, and what it does is it actually compiles these for you. So it will make a Mac version, it will make a Windows version, and it will keep the Linux version. It just makes a source available for us. Sometimes there is a change on CRAN, which they've made the same day, and they haven't had time to build the binary for you yet. So the Windows binary is not made. Maybe it takes a few days. Remember, there's 3,000 packages in CRAN, maybe more. So they have got a few build machines, and every day someone makes a change, they try and build them. If you try and install it while it still hasn't built the latest version, it will warn you and it will say, do you want to do it yourself? I always say no. It's never going to be that different. That like day isn't going to make that much of a change. Do I have any more on this here? Typically, packages are updated every 6 months. So there's like a release cycle, and we'll come to this more in Bioconductor because that's where we publish our software. But really, the problem with compiling from source is that most of you won't have the necessary C++ libraries, etc., to compile from source. So it's really not worth. It's really not worth messing with unless you really want to know. And I think I'll talk to you and show you first. Once we've installed the package, we then need to make it available to us. We need to load it. And to do that, we can do library, and then the name of the package here, Rio. There is an alternative here. We could use require, similar functionality. Require Rio will also load it. Inside Rio, we have two main functions, import and export. The import function, we can use, say, just to import a CSV here. And if I do import, I give it a file with a CSV extension, .csv. I don't have to say to it separator or anything. It recognizes .csv and it will choose the right format, choose the right way to parse it. Okay. Similarly, we can use the import function now on an XLS, right? Your Excel output or an XLSX, the very latest format. Okay, in that case, if we're reading a multi-panel Excel file, we may just want to read in one sheet from it, right? So the second sheet. And here we can just do which equals 2. And it's going to pull out the second sheet from this Excel file and return me the data frame limited. I can also use which if I've named the sheet in my Excel. You can have tab names for your Excel sheets. If I say here metadata, it will go and look for the metadata name tab and it will read that. If I want to get all the sheets in to R, I can use import underscore list, give it the Excel file I want to read, and then what I get back is a list of data frames. Okay, and the list will have names. So I've got an element, or the number of elements in my list will be the number of sheets in my Excel file. And in this case, I've got one sheet which was expression scores and a second sheet which was metadata. Because this is a list, we can use our friendly list extension, list accessors, dollar or this double square brackets. So here I'm going to do table dollar expression scores, and I can get just the expression scores data frame. Similar dollar metadata, and I can just get the metadata. Once we are done, we can also, and this is really useful, export back to an XLS file. In this case, we're just going to change, we're just going to create a single tab XLS. So I'm just going to take the expression scores data frame. And to export it, all I need to do is export from the Rio function, give it the table I want to export, and tell it the file name I want to export to. And in this case, I'm going to export it to the latest version of Excel, XLSX. We can also export multiple data frames into one XLS. So if I want to give my PI, my collaborator, all my results in one XLS file, I just need to create a list of data frames to write out. I need to assign some names, and these will be the names of the tabs in my Excel file. And here I'm calling them expr and meta. And now just export table, give it the file I want to write to, and then I will get a valid XLSX with multiple sheets containing my data. So I never used to be a big fan of XLSX or Excel format until I discovered Rio, and it's great to be able to pass someone one big Excel file with all your results. So I think we've reached the time that we can probably jump into an exercise. I have some exercises here now on reading and writing data. It's not too long, so don't get stuck. There are like a little bit of tricks there, and I think I've added this trick of the comment character. So David's in the room, he's at the back. I'm in the room as well. Feel free to just work through this, and you should be able to, if you get stuck, just come to the answers here. So we had this kind of at the end of the last session, and I didn't really chat. I'm going to come to the chat in a second. In order to work and to read in this data, if you want to follow my answers, we're going to need to set the working directory. And I think I said this in the very beginning of my class, but I think you asked me to show it again. Right? So this is the first time we're reading in data, so we need to be in the right place on the computer. So I'm going to set my working directory, and I'm going to do, there are some really easy ways to do it, but here I'm going to do choose directory. And I did it in my downloads, so I should have downloaded them yesterday. There we go. Downloaded it multiple times. It was inside here. Good. So if I set myself to that directory now, I should be able to do read.delim. And now if I can do data, am I in that right place? Data. So now I'm in the right place, and the answers will actually give you the right path. Okay, so I'm going to give us an hour or so, and then my next session will start at 2:30, and I'm going to do conditionals. So we're going to do if and loops. I'm going to stop. I'm going to answer the question first. Oh, thanks. And I'll pause this. Great. So I was going to run through some of the solutions quickly for these exercises for reading and data. I can tell you in our next exercise, we're going to be looping reading data and merging into bigger. Important that we get an idea of this. Have a look in Notepad or Excel for attempting to read the files. That can be found in the data directory. So we're going to look at this gene expression.txt file, gene expression with methods, with notes, and this gene expression. Have a quick look at them. We should be in the data directory. So gene expression looks fine. It looks like it's white space separated, tab separated, I think. So that should be straightforward. This one has, this is with notes, with methods. So we have 3 lines here describing, I guess, what happens with the data. So a lot of systems, a lot of programs will kick out a file like this. We know the first 3 lines we don't want. 4th line is the column headers. That was methods, then notes. Yeah, very unfriendly. Someone's made some notes in the middle of the file. So that's also a bit of a pain, right? So we should be able to deal with reading these in, hopefully friendly with this. So read in tab delimited file, the expression.txt. So we can do read table. We just need to do the path to the file. If you set the working directory, or one directory above the data directory, data / expression. Header equals true, so I just put H equals true here. True. Separator, I said it was tab delimited, so we can use the tab separator here, /T, to signify a tab. And then we'll use row names equals 1. If you look at the file, you know the row names are really want. Once we've done that, find the mean expression of all samples. So we could do it this way, right, using mean and do the mean of each column separately. But because we've read it in and we've actually put the row names straight there, right, they're no longer a column, we can actually use the function, and we saw this in our first session exercises, col means directly on our data frame, and it should just give us the same result. And I don't need to assign any names to them because it will just take them. Read in the tab with methods. So I can't remember which one the with methods was, but I guess it's the one which had 3 lines we want to ignore. So then we can just say skip equals 3. It's going to skip over those lines, not read them in, and then it will just read in the rest of the file. Still setting row names to be 1 and the rest of the parameters. Okay, it's just I went and looked at the file. I want to miss the first 3 lines, so I add skip equals 3. Read in the tab delimited file gene expression with notes.txt. This file contains notes about particular genes. Okay, so now it's not in the first 3 lines. We can't just skip them. They're randomly spread out throughout the file. So we need to skip anything which has a line starting with this. I looked at the actual file, which is greater than sign. I think by default, there is a default for comment char. If we want to look at the read table help, it will tell us. Comment char by default is this hash. So any hashes in your file, any lines beginning with hash, will just be ignored on the reader. This could be a problem if you actually have hashes in your file and you want to read that particular line. It will send you insane working out why it's not. It's because by default, any line beginning with hash. And that's kind of a programming, generally a convention. You know, we have, we're not doing this yet. We'll come to this in reproducible R. But if I have a line like that I want to run, I can also comment out lines and they will no longer evaluate if I put a hash in front of it. So it's kind of a common feature, I guess, in programming is a hash means ignore this line. So by default, a hash in the file will be ignored. What was the last question here? Read in tab delimited file gene expression.txt order genes by decreasing the expression in sample 1. Great. So, because yeah, this is good. So read table in, we do it standard way with row names. And then order it by a particular column here, right? So I select this column, I pass this to the order function, but I also say decreasing equals true because by default it will go the other way. And then once that's ordered, before I write it out, to avoid this problem I showed you of having shifted header labels, because the row names won't have a column name, I c-bind the row names back onto the data frame, and then I write it out. Okay, does that make sense, that last bit there? Let me know around, we can discuss it. Effectively, this is just a little example of what you would need to do to write out a file but maintain the row names. You need to create a new column by c-binding the row names to your data frame. I assign a name to that column now. It's now the first column in my data frame. And then I write that out. Column names equals true, row names equals false. I don't need them anymore because I've attached a column here of row names. No. Let's run that quickly so we can have a look. Ordered expression. Now ordered decreasing equals true by this column. Before it wasn't. And then I'm going to c-bind the row names back on. Here, you can see it gives me a really rubbishy name for my column. So I'm then just taking the col names, I'm actually just going to replace the first one. I'm going to replace it with G names. So then I have a much more sensible file. But when I write it out, I want to get rid of the row names now. I don't want them to put my whole file out of whack. So I'll write this out, but I'll say row names. Should have popped up in your actual working directory. If actually, one thing I didn't show you, if you don't want those quotes around your names for whatever reason, remember Excel will ignore quotes, but you can do quotes equals false. And then you can see we don't get these quotes, depending on what you prefer. Excel will just ignore quotes. Okay, so that's the end of session 1. Fantastic. We're now in session 2, so this is just the second session on this page. And here we're going to cover a little bit more like functional programming in a very light way. We don't need to do much programming for this class. We just actually reading in, manipulating data. We're not necessarily writing big, complex scripts. More of an interactive language, I would say. And one of the first things we want to get a handle on, which is very useful, is conditions and loops. It's the nice thing about any programming language. We can say, given a certain circumstance, do this. Across 100 files, apply this. Why it becomes better than just doing it. So I think we've already looked at things like logical vectors. So we've done x is great, lower level, x is less than 4. I'll just maybe write this out somewhere. So this is a bit at the bottom of the screen. So, you know, we have our thing, and if I want to turn this into a logical vector, do this, and it's going to give me all the values less than 4. And already we can use this in some way to make a choice. We can use it to subset our files by all those which were less than a certain. So we've already come across logicals, but we can also use logicals now to decide, shall I run this script? Shall I run this particular procedure? Or shall I run this other procedure? So the two things we want to learn here are conditional branching, if this, else do this, and loops. Right? While I'm analyzing data, if I need to execute something complex, I will use R. In other cases, else, I will use a calculator. So conditional branching is just the evaluation of a logical, a true or a false, to determine whether a chunk of code is executed. Right? And then to control whether a piece of code is executed in R, we use this if statement. We use an if statement, and then we follow this if statement with brackets like we would a function. And within that function, we will have our logical to determine whether the code in these curly brackets is evaluated. So let's put this into action. We'll make x equals true. If x, and we know x is true, I've set it to be true here. Message, and this is going to print a message, x is true. This is our little bit of a script here. I've set x to be true. Therefore, this message is going to print, and we can see here x. If you ever want to print anything to the console in R, message is the way to do it. Don't use print, don't use cat. Message is the way to do it because message can be controlled and suppressed. You can turn off messages in R. You can't turn off printing. So now if I set x to be false though, so this now will be false in here. If this is false, message this. Because x isn't true, we've set it to be false. This message isn't printed. Okay. So, you know, this is a very daft example, but we'll start there. X is true. In this case, if this evaluates to be true and here set to be true, it will do the message, and it does. If we set this to be false, nothing in these brackets is considered. It just skips over. More often, we're not going to be upfront setting true or false. We want to do some evaluation in our script. And then in that case, we will actually check a particular condition. So here our condition, we will set x to be 10, we'll set y to be 4. The condition we are evaluating within the brackets here is x is greater than, okay, so x is 10, y is 4, so x is greater than y. It should go in and it should evaluate what was between these curly brackets. And here it should print, which it does. The message, the value of x is x, 10, which is greater than. Great. We then turn this and make y greater than x. So in this case, I'll set y to be 20, x stays as 10. When this is evaluated now, if it will look at this statement and it will say, well, x isn't greater than 20, therefore I just skip everything inside the curly brackets. So we don't get that message printed. That's the concept of logicals in R. It's very simple. We want to make this a little bit more complex, though. What happens in the case of x being greater than y? For us, we don't see anything. Right, so we might want to catch that condition too. What happens if x is less than y? So we can do that by using an else statement. This is the most basic way of doing it. And an else statement will capture everything else. Okay, so in this case here, if I set x to be 3, first off, it will check whatever is inside this if statement. If this turns out to be false, it will then skip down to the else statement. But else will always be evaluated if this is false. Okay, so this way we have a catch-all for the other side. So in this case, I've set x to be 3, message x is less than 5, is less than 5. Okay, else do this other thing. We know x is less than 3, so it will go in here and evaluate the first one. It will skip the second. If now I set x to be 10, this is false, so it won't evaluate this part. And then it will say, okay, what's the option, the alternative? It's the else. And then it will give me the other message. So we can have an if, anything which is true, evaluates to true in there, will come and run this. If this evaluates to false, we will then run everything else. And then start to build this up into very complex conditions. I should add probably something on switch here. But most of the time, this will allow you to evaluate your. So in this case, we want to assess whether x is greater than 5, but we also want to check, is x exactly 5? And we want to do something if neither of those two conditions are true. So this is kind of an order of evaluation. First off, we'll check, is x greater than 5? If it is, we'll provide a message. Else, if x is 5, do this. And we can carry on building up more and more else ifs. If else if is 4, do this. If else if is 3. And finally, we will end it with an else statement. And the else, nothing else is evaluated to be true. This is then what we've done. Okay. So already you can have some quite high level control over evaluation of different conditions. A really useful function, and I promise you this will be a very useful function in your work, is the if-else. What this allows you to do is apply a logical operation to a vector, but not just one value, because here we're always just checking one value at a time. This allows us to assess a whole vector, and for every value in that vector where it assesses to be true, it will give us the first action. So in this case, it's just going to provide, it's going to return a string less or equal. And here is the alternative action, the else, and that would be more. Okay, so what we got here is x is 1 to 10. We got it there. I'm going to assess for every condition, so every index in my vector, I will check whether or not it was less than or equal to 3. So 1 less than or equal to 3, I get that result, less than or equal. 2 is less than, 3 is less than or equal, less than or equal. So for the first 3, I'll get that result. For the remainder, I will get more. Just assessing for every element here, is it less than 3? Return me this if that's true, return me that if it's false. Okay. So it's actually a really nice way of turning I think this is exactly what we'll do. You can turn a number into categories this way. So if it's less than that, call it small. If it's greater than that, call it big. And of course, you can make this nested too, make this as complex. I don't know how complex we get it. We'll make it as complex as we need to be. So in this case, we have a first condition we want to assess. So for my long vector here, 1 to 10, I'll go if else x is equal to 3, call it same. If it's not equal to 3, go down to our next level of assessment and tell me whether it's less than 3. And then sign it less. Else, sign it So here we have our evaluation. What happens if it's true? And then the what happens if it's false? We have another evaluation. So we can know in this case, it's going to go through first number 1, it's not equal to 3. I will go to the if else, and then I will check whether it's less than 3. If less, I will put less. If it's more, I will put more. So for the first 2, it's less. For the third one, x equals 3. So it says same. And then for all the other ones, it's not true here, it's not true here. So it's going to give us both. Slice check if else, and you'll basically apply to a numeric vector function or a logical evaluation to stick out the result. So the next thing we want to look at here is how we can perhaps programmatically move through our data. So obviously the most useful thing here is for programming is the fact that we can write a script, a procedure we want to apply, and then we can just set it running on the hundreds of files we have. Ideally what we'd be able to do. So in R, we have probably multiple ways, but the 2 main ways of looping through things are while and for. Most of the time you're going to be using for loops, but while also has some use. So while will loop through a particular piece of code, it will keep evaluating some code until the condition evaluates as true. While the condition. So while someone hasn't turned up, keep waiting. When that person turns up, I will stop. For is going to loop through a range of values, applying particular script, function, set of procedures for every one of those values. So often we will use this because we will have, say, all the files in a directory, dir. We'll say dir, give me all the files. For every file in the directory, read it in, organize it, remove this column, write it out again. Go to the next one. Okay, so for tends to be what you'll use more. But while is an essential. So we'll start with while. Okay, so in this case, as I said, while loops will continue to evaluate until this condition comes out as false. So they're most useful, in fact, they're only really useful, if we know eventually that condition will be true. Okay, I can tell you we're going to do an exercise, and some of you in this class are going to get this wrong. Your computer is going to continue looping, and it's never going to evaluate to be true. It's a good lesson to learn, and we'll learn it here today. In this case, we just got a really simple example. We set x to be 1, and I'm going to say while x is less than 3, message what x is effectively. So I do, this is a bit of the string I want to print, comma, I can put in a value here and it will evaluate what x is, a bit of a string. And then once I've printed this message, I'm going to increase x by 1 value. So I'm going to add 1 to x. So the first time it comes through the loop, it's going to go x is 1, 1 is less than 3, it's going to print the message, x is 1. Then going to add 1 to x. So now x is 2. When it comes through again, 2 is still less than 3. It's going to print that message, x is 2. And then it's going to perform the next line. And it's going to add 1 to x. So x is going to become 3. And as it comes through the loop the third time, it's not going to be true anymore. 3 is not less than 3. So it won't do this message. The really important thing of this while loop is that this line exists. Okay, if I remove that line, x will never be greater than 3. So it will just keep on going and keep on going and keep on going. Okay. At the end of this, I've added a message just to say. We got a nice example of that in our Now, for loops allow the user to cycle through a range of values, applying an operation to every. So here we're going to have to cycle through a numeric vector. This is on my screen, 1 to 5, and we'll just print out every value as it goes. So the setup here for a for loop, I'm surprised I don't actually say that, is to go, so we have here x 1 to 5, we'll do for I in x. So it's for I in this range of values, loop through them. And what it does is for every value of x, it will assign the value to I in order as it loops through. So the first time it goes through the loop, it assigns the first value of x. So x becomes 1. Right, because x is 1 to 5 here. And we'll get message 1. Then I put append lf. This is line end. So it's just going to put it in a row for us rather than new lines. And then it comes through the loop again. It's got more values. The second value will be 2. It's going to message that. Third value will be 3, 4, 5. And we'll just get them all printed out. Once we've got to 5, it's done. And it will just continue past the loop. Loops do not need to just work on numbers. Right? So we can loop through anything which is an ordered collection. Vectors, lists, these are ordered collections, right? So we have a first element, a second element, so anything like that we can loop through. So we can loop through letters. Okay, so I don't know if you know this, but I think when you load R, you have a few objects available to you just to allow you to play around with, and one of them is letters. You also have capital letters, which is capital letters, okay, as well, right? So they have like little things you can kind of pick out. I really should have just done that, but in this case, I've used letters. I've made them uppercase. I've just taken the first 5 letters of the alphabet. Effectively, letters will return the alphabet, however many in the alphabet, and it'll just allow you to kind of work. So here I've just taken the first 5. I'm going for I in the first 5 letters of the alphabet. Message, you can see. Often, we kind of want to loop through multiple kind of vectors which we know are in the same order at the same time. Okay? So let's say for whatever reason I have a vector of gene names and I have a vector of expression. So you can imagine in a file, you know, your rows, you would have one column, you would have gene names, expression. In this case, we just have 2 vectors side by side. I might want to use a little trick we have here to kind of loop through both of them at the same time. So I know they're the same length, so I could actually just pull out a vector which represents the indices 1, 2, 3, 1, 2, 3, 1, 2, 3. Actually, it's just telling me the indices of every value or every potential index within my gene name or my expression. What I would then do is loop through not necessarily the actual gene names themselves, but I would just loop through the positions. So here I'm going to do 1 to length gene name. That will give me 1 to the total length of that vector, 1, 2, 3. And as I loop through, I will look up the first index first time through of gene name, and I will look up the first index of expression. So it's going to look up XZF1 here, and then it's going to look up the equivalent expression value from my expression vector there and print that. Okay. So often you won't just be looping through directly on the object you want to operate on. You will be looping through the indexes of the object and then applying. Okay. See where I am. Now we can start to get complex and start to kind of stick these two together. So I showed you a little bit about if-else, and you can actually accomplish this probably with an if-else as well. But in this case, if I wanted to loop through a set of numbers and then do an evaluation for every loop, of course, I can start to combine these together in R. This is a nice, very simple example, but here we have x 1 to 13. So I could say for I in 1 to 13. Right? So I'm going to loop through this 1 to 13 value. As I go through the first time, tell me whether or not I is greater than 10. If it is, print this. Else, if I is 10, print this. Else, do this. And then continue back through the loop. And it will just continue through the loop for every value of x, which is 1 to 13. So it doesn't quite fit on the page. You can see the first time it comes through, I is 1, therefore that's false, but in case they're both false, we'll go to the else, we'll get those printed all the way up until 10. When it came through the 10th time through the loop, and I was 10, then this evaluated to be true. This was still false, else if I equals 10, yes it was, then it would evaluate this message. After that, I became 11 on the next iteration through the loop. And then I was greater than 10. So it would print this first message. And then it would ignore the second one. And so we can very easily just combine for loops. And inside a for loop, we can do any operation. So why not? We could do an if or an else. You may want to use conditionals to exit a loop if a particular circumstance has. And I haven't really chosen a great circumstance here, but let's say you're searching through files, and if you find something, you then want to just stop. You've finished your operation, and you want to print it. You can use this break function to make a for loop a little bit more like a while. But actually, because you have conditionals here, it's a little bit more powerful. So in this case, in the if I equals 10, as the last thing within this evaluation part, within these curly brackets, I put break. And what break does, it will tell it to exit from the current loop that it's in. So you can see here, we are going 1 to 13. We should have got to this point and it evaluated I equals 10, printed the message, and then it read the break, it left the loop. And even though we had another 3 values to go through, we never got to see them, right? So just break kills that loop. Okay, how are we doing for time? I think we're doing very well, actually. Okay, so we have unlike some programming languages or other programming languages, because it's a little higher level, it has some really nice wrappers for kind of the loop functions. So we don't necessarily need to write for loop. We have 3 functions available to us, really major functions. There are more, but these are apply, lapply, s. There are other ones, mapply, as we get to specialist objects, there's prapply, etc. But these are really the main ones. So I'm going to say up front, there is no speed advantage to using apply, lapply. They make your code neater, I was going to say prettier, probably neater, easier to read, because you don't have these long, potentially poly clauses. But there is this illusion, people seem to think that these things will make your scripting faster. There's no way, it can never make your scripting faster. It is effectively under the hood passing it to a for loop for you. So I think these look neat in your code and easy to follow, but don't get hung up on doing them thinking that they're going to make stuff faster. They're not being compiled into another language. Still being evaluated. There are ways to make things faster. So if we go through this family, we have apply. So apply is really for matrices or data frames. And it allows you to apply a function, let's say mean, to every row, column, or actually every single cell of a matrix or a data frame. And it will return the results as a vector, matrix, or list. lapply, which is list apply, applies a function to every element of a vector or a list. So it goes through every element of your vector or list one at a time, applies the function, and returns the result for every element in the list as a list. So the first results in the first element of the list. sapply is a fantastic function, smart apply. Yeah, and actually it really does do what it says on the tin. So supply, we'll show you it. It will take a vector or a list, so it's like lapply, but it will return the results as a vector matrix or list, and it actually has an order. So it will try and return your results as a matrix. If it can't return your results as a matrix, it will try and return them as a list. If it can't do that, it will return them. Sorry, it will try and return them as a vector. If it can't do that, it will return them as a list. Hard to explain this, but I'm going to show you. Effectively, it's going to try and make some decisions. It believes that you wanted a matrix back based on the format of the data. Let's start with apply. Apply function applies a function to the rows or columns of a matrix. It can be cells as well. The argument fun specifies the function to apply. So that could be mean, sum, all these functions. Like read dilemma. And the margin is whether or not to apply the function on the rows, columns, or the individual cells. So here we have apply. This is the matrix, the data frame we give it. This is whether or not we want to work 1 for rows, 2 for columns, or individual cells. We'll give it a vector C12. And then this is the actual function we want to apply. I think I'm going to describe what goes here. Next few slides. Okay. So let's build a matrix first. Make a matrix. We can go 1 to 4. N row equals 2. N col equals 2. I want to go by row equals true. So it's going to go 1, 2, 3, 4 when it fills it, rather than 1, 2, 3, 4. It wasn't by row. Now I can apply my mean function on my matrix, and I want to work by rows. Do 1. You can see it gives me the mean of 1 and 2, and the mean of 3 and 4. If I want to go by columns, I just change this to be 2, and then I will get the mean of 1 and 3 and the mean of 2 and 4. If I put in here, I don't think I have it. If I put in here C1, comma 2, it would just apply it to every single cell, which would be useless here because I would just get the mean of a single. That might be useful if I want to apply, say, log or something. There we go. So additional arguments can be passed in this ... When you see this, it usually means additional arguments can be passed to the. So if I have a function like paste, just do question mark paste. I think we used paste before. Concatenate vectors after converting to a character. Paste has at least 1 or 2 really useful functions, and one is sep. And it's kind of the string which is going to use to separate the things it's pasting together. It also has collapse, which is when I give it a character vector, it's going to try and connect all the points in the character vector, and it's going to use this collapse character to connect. So let's try that in action. Paste letters, do collapse equals colon. See, it's going to put a colon between everything. The difference there with sep and collapse, if I do sep equals, see, it has no effect. But if I want to paste 2 separate vectors together, somewhere in the middle of the, you can't see my comma. It should put, oh no, it won't do, sorry. Yeah. There we go. So there's a slight difference. Oh, sorry. Sorry. I like to pick on R as well for some of their choices. R is inherited a lot from S, so this is a slight problem. Hopefully the R gods aren't watching this soon, but they've had to kind of inherit some functionality, and it's followed them around for like. The other side of this is the kind of tidyverse. I'm not sure if you know any R, but you do know of the tidyverse. The tidyverse is like we have a course on it. I don't teach it because it's not mainstreamed this, but I'm happy to do it. So tidyverse is a set of packages which allow you to do. They believe R is kind of wrong in some of their choices, so they don't use paste. They have the string R package. This concatenates things in different ways. They don't have plot, they have ggplot. They have clever ways, and they've decided base R was a little wrong. They tried to fix it. I can tell you tidyverse is great, but not everyone uses it. And the worry for me to teach this is you will get to a situation you'll be following a manual. The manual will always have base R. It won't use tidyverse. I'm not sure that quite captures your question, but we can come to your question. So I think it was good. I just don't. So in this case, paste is a function for putting things together. If we want to operate on every row here, I need to give it another argument. So paste wants another argument. It's a function. It itself takes arguments. Okay? So in this place, I want to apply the paste function to every row set by 1 of my matrix, and I want the collapsed argument passed to paste to be clear. Okay, so if I have any additional arguments I want to apply pass to this function, I put them after the comma. After. This means we're allowed to do a little bit more complex. lapply applies a function to every element of a vector or a list. So lapply is actually what I use the most. And there are parallel versions of lapply, BIOC parallel lapply, which allows you to use every core on your computer or every node on your HPC. And it will send off every element here to a separate CPU or a separate. So in this case, this is a really rubbishy example. I'm going to do lapply, and I'm going to take the mean of this element and this element. So the mean of 1 is 1, the mean of 2 is 2. That's the first example. But as with apply, I can also provide additional arguments. So this is our standard setup. If I need to apply any arguments to mean, pass any additional functions, arguments to mean parameters, I can do comma, and I can supply them after there. And in this case, I'm saying na.rm equals true. And this is just another way of us dealing with these na values. So where we don't really have a number. And in this case, you can see our second element of our list, I have an na. Mean accepts an additional argument, na equals rm true. It just ignores the na, its calculation, and takes the mean of it. So we can apply lapply, and we can pass additional functions. What's important, though, is that lapply gives us back the list. Okay, so then we need to start to work out, okay, in this way you can come to the idea I showed you earlier on of flattening lists and turning them into matrices. Right? You want to then turn it into something you want to work with. How many slides have I got left? So a really nice function is this sapply, which is smart apply. It acts like lapply, but it attempts to return the results as the most appropriate. So in this case, I'm going to do sapply, take the mean of either this vector or this list. Okay. So if I do sapply on the vector, take the mean, and I'm going to just keep this NAR. It's true. No, it doesn't do anything here. I get a vector back. I don't get a list back like lapply, I get a vector back. If I do it on a list, right, it's not going to give me a list back. It's going to give a vector back. So it's going to act like lapply. It's going to try and give me something simpler like on a list. It would give me. a really useful example of lapply here is here. So here we have a list, and I have a list of names: row 1, row 2, row 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If I do lapply and just want to get the quantile from this, quantile is going to return 5 values. It's going to return my tiles 0, 25, 50, 75, and 100. If I do lapply, it gives me a list back. Right? For every row or whatever I gave it here, it gives me a quantile, and then I get another element. So I get a list named by the elements I gave it, a list back. If I apply sapply here, it actually does something kind of clever. It's put it straight back into a matrix. So I do sapply, I give it quantile, and it knows that these things could be turned into a matrix where the columns are rows. It's assigned my row names there based on the results from here. Let's try to put it into what is a table. So sapply will try and start with giving you back a table. If it feels that everything can be put into a table for you, and typically if lapply would return a multi-length vector. All the vectors are the same length. It's going to try and give you a table. If it can't give you a table, it will try and give you a vector. Right? But if it can't do either, it just results back to vector view. So if I do sapply and I give it here a list, and the first one's a data frame, the second one's a vector, and the third one's a vector, the result for summary on each element of this list, summary on a data frame gives me something quite different to summary on a vector. So there's no way to stick these back together into one vector. There's no way to make a table out of them. So sapply tries to give us the simplest kind of object it can, which is here. So it gives me them named again by the objects I gave it here, df. Okay, so we're a little early for the end of our session now, but I think this is all we can cover today. It's a lot here. I can tell you now we have quite a tougher exercise. There isn't actually that many questions, but it's not straightforward. And it's certainly got one of the most useful exercises, which is read all the files in a directory, put them together, and create one bigger file. I can tell you that's a really useful thing to do in R. Get all my files here, manipulate them a bit, make a big object. So work through these. I will come back and we will run through these, I would say 4:15. If you want to leave at this point, I will be on Zoom. This is all being recorded. So I can add you will have the answers and solutions, and I will run through them there. Absolutely up to you. But I will be back here at 4:15, David, to run through these solutions. These are a little tricky now, so if you have any questions, definitely stop me and David. So we've got to our questions. Hopefully you have the questions here. Conditional looping and branching. A few questions about effectively just looping to make a factorial. We have an if-else question, which is hopefully not too tricky. And then we had a tricky question, which was the looping through files from an expression directory with a doctext extension, create a table of the gene expression. Actually, the solution wouldn't have got you there. The solution, so I fixed that. It would have got you there, but it would have got you there one step too early. An annotation from annotation.text. How do the pathway information from genes compare? And all we were going to see here is there was more in the original annotation table than we had. So let me run through the solutions. the first one was calculate the factorial 3 equals of 3, okay, of 10 using a loop, and that's what a factorial actually is. Obviously, there is a function inside R and base R to do factorial, which is why when I first did these classes, I had to add in a loop because most people just found the function around it. So if we're going to go and try and find the factorial of 10, we know what we're going to have to do. If factorial is 3 times 2 times 1, we know that the limit of our loop will be 10, right? So we know we're going to go from 1 to 10. So I'm going to create a vector here, 1 to 10, and then I'm going to loop through it. So in this case, I'm just going to start my loop with 4x in 1 to 10. I think in my examples, I'm using I. It doesn't matter what that variable is called. Whatever we call it here is going to be used throughout the rest of it. Temporarily, within the for loop, x becomes the values of 1 to 10. In this case, we just need to have one if else, and maybe there's another solution if someone's found here. But in this case, I'm going to go in the first time we go through the loop, so that will be when x equals 1. That first time, I will set my factorial answer just to be 1. If it's not the first time through the loop, so the second time it comes through the loop, factorial answer now, x is not 1, so it's going to skip this, and then factorial answer is factorial answer times by whatever the loop is. So the second time it's 1 times 2. When it comes through the third time, it will be 3 times. And then the fourth time, it will be 4 times the result. So effectively, we're looping through 1 and 10. We're just making sure the first time we go through, we assign this variable to be 1. And then every other time we go through the loop, we times that variable by position we are in the loop. We just keep on adding it on as we go. So our factorial answer ends up being whatever this number is. It's quite common. First time you go through a loop, you often need to do something different than you would the other times you do. Adjusting the answer from before, what is the first number which has a factor greater than 10,000? Okay, so we need to set some things up front because we're going to go through this loop, and I'm going to be assessing in the while loop whether or not factorial answer is less than or equal to 1,000. It's greater. I'm going to set factorial answer to be 0 to start off with. I'm going to set count to be 0 to start off with. And then we'll set our loop while this factorial answer is still less than 1,000. And this is why I need to set factorial answer here. I already have a solution up here, so I need to make sure I reset it. But if I don't set factorial answer, first time it comes to the loop, it will say, I can't find an object with factorial answer. And then it will just die. And so we need to set that up front. I'm also going to set my count to be 0, and this is going to keep track of actually how many times I've been through the while loop. So I'm going to set while loop, while this is still less than 1,000, I'm going to add 1 to my count. So this is the first time I'm going through the loop. And then it's the same as my for loop solution. I have while count equals 1, which is the same as up here. Set factorial to be 1, else factorial answer is that times the count, how many times I've been through the loop. Count here previously was just established because I was looping through 1 to 10, and x was effectively my count, the number of times I've been through. At some point, the factorial answer here will get higher than 1,000, and it's going to come up here, and it's going to break, and it's not going to print it. So the count, the time when it actually broke, is going to be first time that it's greater than 1,000. So if I check that, factorial 7 is 5,000, factorial 6, 700. So I'm just making sure, really I've just turned that from above, had to include my own count for how many times I've been through the loop. And then my factor, my while is just make sure it's going to break as soon as I break this condition. Using an if-else expression, create a factor from a vector of 1 to 40, where all numbers are less than 10, small, 10 to 30 are mid, 31 to 40 are big. So I think I said this would be a use of if-else. So we have a long vector, 1 to 40. I want to assess every position in this vector. I could do it in a for loop. Here I've said use if-else. So if we break this out a bit, first thing we do is if-else, and I'll check whether or not any of the positions are less than 10. If they are, I'll label them as small. Okay, so in the true situation where that's true, they'll be labeled as small. If they're not less than 10, they will come down then to the second level of evaluation, and they will then check, are they less than 31? If they are, they'll be labeled mid. And finally, this is our else part of this here. There is nothing else to be evaluated, so it's then going to place them to be big. So if I do that, we'll get our vector result. And it's just a standard character vector here. It turned everything less than 10 into small, and then everything less than 31 became mid. Everything less than 31, which didn't already pass that. And then everything else, the else became. That's pretty good. And if we wanted to turn that into a factor, we could just do factor vector result. The problem there is it's taken the alphabetical order of our factors. And the alphabetical order is almost exactly what we don't want, big, mid, small. So what we have to do is set our own levels, and I'm going to set them to be small, mid, big. And I'm going to tell it then this is an ordinal factor by saying order equals true. So then, you know, I could do the temp 1 is less than temp 37. The categories now have order, whereas before, if I took that order out, it would just give me a nonsense answer. It says it's not meaningful for this. Okay, so the final part here is the tough, and it's a question I recommend you make sure you understand, because it's just useful to you anyway. But we will do this same exercise again and again under slightly different variations. We're going to read in heap files of DNA binding. We're going to read in gene expression matrices and put them into model. So the solution, did anyone look at the solutions for this? Okay, so the solution had an error in this. There's 2 people who teach this class. I'd love to blame the other guy for making this, but it's probably me. So in the original version of this, effectively we had, and I say it here, read all files with a .text extension from the expression directory. Okay, what shouldn't have been in there is annotation. That's not an expression. I think it was missing last time we ran it. So if I do this, files to read, it lists it as one of the files to read. And that's because, you know, I could just do this, I think. It's got a .text in it. It's got text. That's an issue. What would get us around it, the expression files here have expression results underscore in it, and annotation doesn't. So I can use this pattern. It's just going to look for a file which has this in it. If I do that, that should work. So then I'm avoiding this annotation. That's my mistake. I will fix the solution. Actually, the solution did work. It just meant you didn't need to merge in the annotation file as a second part. Okay, so given we're going to read in these files, what I'm going to do then is create a list to assign my files to. Here I'm creating an empty list. Also do file read. I can also create empty lists this way. If I do this. Still gives me length. I can create empty lists various ways. Here I'm creating a vector of a list. I'm saying it needs to be the length of the name of the files. In the first part, we're going to do this, and there are lots of different solutions to this. Just one. First thing we'll do is we're going to loop through the files we need to read. So files to read. I'm going to loop through them. Here I'm doing that trick where I'm not looping through the files directly. I'm looping through the index of the files. 1, 2, 3, 4, 5, 6, 7, 10. And I'm doing that because I want to assign them to an element list. So if I read the first one, we can set I to be 1. First one we'll read in. It's tab separated. It doesn't have a header. Yes. So I have to set header equals false. That gives me this little data frame. And it's then going to actually assign it to the first element within here. The last thing I want to do, because it doesn't have column headers, is I want to give it some sensible column headers. So I'm then going to give it a column header. So effectively, I'm giving it the column headers, gene names, and then the second one is the name of the file I've read in. This is a very typical thing. You're going to read in the file, assign a column name to be the name of the file you read in. And then when we concatenate them together or merge them together, we know this column came from this file. So we'll just do that in one go now. Now I have a list, and each element in my list contains a file I've read. So now we need to put them all together. So we're going to make the assumption here that these files aren't in the same order. Right? So I could get a file and it's not ordered gene 1 to gene 5. That's something you should always assume they're not in the same order. So we're going to use the merge function, select a column we want to merge by, and then we're going to write that back. So the first thing I'm going to do is set an object to be empty. Merge table here is null. And then I'm going to read or loop. And I could set this to be anything. It's just I need this conditional. So the first time we go through a loop, like above, I want to do something different the second time I go through a loop. So for I in every file read in, so every element of this list, if merge table here is null, I could also just set it to be empty or something. If it's effectively hasn't been set yet, set merge table just to be the first in the list. So here, as we go through, I takes on each element in our list. And as we go through, first time merge table is still null, then it just assigns that element of the list to the object merge table. Carries on, it tells us the number of rows, we print the number of rows. Then it comes in a second time. This time I've already assigned merge table. I did it here. Right, so I gave it an element from my list. Now merge table is no longer null. It goes into the else, and it merges merge table with the next element in the list. And here it's using the first column. And it goes through again. Merge table is now still not null, right? We've set it to be now this way through. So it ignores this and it adds in the next element of the list. And it keeps on looping through the list until it's created, hopefully, our big kind of merged combined table. Ooh, what did I do there? 1, 2, 4. So just go through read in every index, merge it through the current table with the data. So at the moment that just has gene names and then a column for every expression sample. We then wanted to add in to this some annotation. And this again is going to be something you will do typically. You will get some results, but then you want to add additional annotation for genes, what pathways they're in. So now we have our annotation table. So I can already look at this table, and this is my gene names as the first column. If I look at my annotation, it's also the first column. It's also called gene name 2. It's not called gene names. This is called gene names. This is gene name. So we saw that if they're called the same name, we can actually set by to be a string. Right? But in this case, this is called gene name and rather unfriendly. This has got an S on the end, so we can't do that. We have to go by, and we'll say the first column. I say don't keep everything in X, so don't keep everything in the annotation, but keep everything in my merge table. That's also quite common. Often if you're going to add annotation to your results, you really care about what was in your table, your like expression values. But if you're using a massive database of annotation, they may have genes you've never heard of and just aren't useful. So in this case, we're going to keep everything in our table, but we'll throw away anything which was in the annotation table, but not in ours. So that gives us this, where we have gene name, ensemble gene ID, and then the actual pathway it's involved in. Should be able to, I think because it's annotated expression, maybe if I turn that into a data frame. Annotated expression. So one thing I see what I'm trying to do. So what I'm doing here is just giving you a summary of this pathway, and it's saying that we have, once we've merged them together, we've only got 2,000. Right? So we've lost a lot of rows which were in our annotation, but no longer in our expression. So if we look at the original expression data, we can see we have 5,000 genes, 5,000 rows. So it just means there are a lot of genes in our annotation data that weren't in our table. So once we've merged them. Question. Excellent. Yeah, sorry, Abby. So I have a question there about all X and all Y. So, if we're ever lost, we just do question mark merge. And this is base. So we're going to go look at the base thing. And we have this function. We have these options, all X and all Y. So you can try and read through this and see what it says. Basically, logical, if true, then extra rows will be added to the output, one for each row in X that has no matching row in Y. These rows will have NAs in those columns that are usually filled with values from Y. Okay, so basically, when we have data, in this case, if we have data in X, which wasn't within Y, if I set both of these to be true, we'll start to get columns which have NAs in them when we didn't have any values in them in the Y, in this merge table. So I can show you that actually in action. So it should be now a little longer. So let's see if we actually have any NAs. I'm trying to think of a nice example for it. So in this case, you can see here, I'm going to give you a couple of them now. You can see here that in times now, because I've set all.x to be true, any rows in the annotation data frame where I didn't have a match in merge table, they would usually be thrown away if I said this. I would just keep those in common. If I say true, it's going to keep them in my end data frame, and it's going to put NA where we would hope to have a value. So it allows you to have a complete data frame because there was no result in merge table for this gene, puts NA. Is that okay, Abby? She's still here for the question. Oh, great, thank you. I'm going to end the session today. Is there any other questions? Is there anything I can help? I'll stop my share, and I will